Okay, so we can also think of complex numbers as being vectors because they're points in the plane. Again, we'll think of the wheel as the x-coordinate and the imaginary part as the y-coordinate. So if z is 2 plus 3i and w is 4 minus 2i, one, two, 1, 2, 3. This isn't going to be the most proportionate drawing of coordinates you've ever seen. So z is 2 plus 3i, so 2 plus 3i is up here. So there's 2 plus 3i, and generally we'll just draw a line like that. 4 minus 2i, 1, 2, 3, 4, 1, 2. 4 minus 2i is down here. And there's that vector, 4 minus 2i. So this is z, and this is w. Z plus w is 6 minus I, 6 plus I, right? So 1, 2, that'd be 6 plus I, z plus w is out there. And what's the relationship between these geometrically? Well, if I draw this line here, that's parallel to w, and this line here, that's parallel to z, I get a parallelogram, right? And z plus w is this diagonal of the parallelogram. Z minus w is minus 2 plus 5i, which technically here would be minus 2 plus 5i, 1, 2, 3, 4, 5, minus 2 plus 5i, technically as a number, it's out here. But if we take this vector and we put its tail down where w is, then it would stretch across the other diagonal of the parallelogram. So, and also remember that z is equal to z minus w plus w. So if we take this vector w plus this vector z minus w, you get the vector z. That's one way to think about which way the z minus w is oriented. So the modulus of the complex number is just the length as a vector, right? So we have vectors here. How long is each vector? The modulus is written like an absolute value. So if z is 2 plus 3i, 1, 2, 1, 2, 3, there's z. We want to know how long is this length. That's the modulus of z. But 2 units this way, 2 units that way, 2, 3. So Pythagoras says 2 squared plus 3 squared equals modulus of z squared. So that'll be 4 plus 9, 13 equals modulus of z squared. And so modulus of z equals root 13. Modulus is a length, so it's always going to be positive. So we always take the positive square root there. So z equals x plus iy. Show that z times z bar equals z squared. So z times z bar is the conjugate, so that's going to be x plus iy times x minus iy. And as we showed above, that just becomes this because the inner and outers cancel, and I squared times minus I times minus I is plus 1, so we pick up a y squared. So that's z times z bar. If we think about a point x plus iy, that's z. The modulus is this distance, that's the modulus of z. But then this distance is x, this distance is y. So what does Pythagoras say? X squared plus y squared equals z squared. So a number times its conjugate gives you the length of the vector squared. So now what we've seen before is that 1 over z, you can find 1 over z by multiplying the top and bottom of the conjugate, but if we have z times z bar, equals modulus of z squared, divide both sides by z, and you get this, and so 1 over z is equal to z bar over modulus of z squared. And so earlier we had found that if W is 4 minus 2i, then we found that W squared is 20. So what is 1 over W? The conjugate over 20. So that's another way to figure out what the 1 over something is. So thinking about things in terms of this allows us to think about equations, and so and geometry a little bit. So modulus of z equals r. What does that mean? Well, again, if we think about a point a plus ib, you know, and generally in complex analysis, you switch between x plus iy and a plus ib quite often. We have this, and so that means a squared plus b squared equals z squared. And if I have this, oh, I should have done x and y here. Well, we'll leave it like that. What do we have if we used x and y instead of a and b? X squared plus y squared equals r squared. And what is that? That's a circle centered at the origin of radius r. And my circles are generally not very good circles, but that's not too bad. So one way to write a circle centered at the origin of radius r is just to say, well, modulus of z equals r. And so the modulus can be thought of as a distance, right? The distance from the point z to 0 is a constant. That means we've got a circle. So what about this? Z minus z naught equals r into an equation with x and y. So if we say z equals x plus iy, then z minus z naught is x minus a. As we take this minus that, we get x minus a plus I times y minus b. Y minus b. So z minus z naught squared is z minus z naught, my z's are getting sloppy, times the conjugate of that, which is x minus a plus I times y minus b. That's my z minus z naught times x minus a minus I times y minus b. That's my z minus z naught. So when I multiply this together, what do I get? I get x minus a squared. Because these are conjugates, the inner and outer cancel out. I get x minus a minus I times y minus b, and then x minus a times I plus I times y minus b. So those will cancel out. And then the last thing I get is minus I squared times y minus b squared, which is x minus a squared plus y minus b squared. And so that's my modulus. So if the modulus is z minus z naught equals r, right, what we know then is that z minus z naught squared equals r squared. Z minus z naught squared is equal to this, which is equal to this. So that would be equal to r squared. So what is this? This is the equation of a circle whose center is A comma B, and whose radius is R. So this is a circle centered at Z0, radius equals R. And again, you can think of this term, the Z minus Z naught in the absolute values, as the distance from Z to Z naught is equal to R. So what are all the points that are the same distance away from a single point? That's a circle. So what's the geometric meaning of modulus of Z is less than modulus of W? Well, modulus of Z equals distance from 0 to Z. Modulus of W means the same thing, except to W. So the geometric meaning is W is further from 0 than Z is. So wherever Z is, that's here, you can draw a circle centered at 0 that contains Z. What's the radius of that circle? That radius is the modulus of Z. So modulus of Z is less than modulus W, just means W is somewhere outside that circle. So W could be out here, and then I can draw a circle centered at the origin that goes through the point W. What would be the radius of that circle? That radius would be W. So the modulus of W is bigger than the modulus of Z, just means that W is further from the origin than Z is. But you have to remember that we're playing in 2 dimensions now, not in just one, right? So we're dealing with the plane. Triangle inequality, Z plus W is less than or equal to modulus of Z plus modulus of W. This just comes from thinking about these things in terms of vectors. If this is Z and this is W, then how do we add 2 vectors? We complete this parallelogram and we draw that diagram. So that's Z plus W. So what do we know about triangles? This length is the length of W. This length is the length of Z, because we just take Z and move it up to here. And the length of this part is the length of Z plus W. So what do you know about triangles? The length of any one side is less than or equal to the sum of the lengths of the other 2 sides. So that's that. So that's one triangle inequality. We'll see why that's useful in not this week, but next week. A second triangle inequality is this one, that Z plus W, the modulus of that is greater than or equal to the modulus of Z minus the modulus of W. Keep in mind that this here inside is a real number, right? Because modulus of Z is a real number, modulus of W. So these absolute values are just the usual real absolute values, right? Taking away the sign from a number. So let me just draw essentially the same picture. Here's Z. No, let's make that W actually. I'm going to put Z out here. If W has this radius, then this distance is the length of W. If Z is on a circle like that, then that length would be length of Z. And where does that put my Z plus W? It's out here. And so this has length Z plus W. So what's this thing geometrically? It's the distance between these 2 circles. Right, and I drew it so that the modulus of Z is bigger than the modulus of W. So what they're just saying here is that this length has to be longer than this length. And in this kind of picture, that's pretty obvious, right? Because to get out to z plus w, you actually have to traverse this whole thing, and that's the length of this. On the other hand, if z and w are actually diametrically opposed, so suppose w is here, and then z is on the same line but out here, then what's z plus w? Well, this is positive, this is negative. Z plus w is actually going to be on this circle there, and a circle for w. Z plus w would be, well, if this is the length of w, then the length of z plus w, well, this is the length of z, then z plus w would actually be, have this length. Right, because z plus w, if w is diametrically opposed to z, then it's the same thing as z minus this particular length is what z plus w is. So the length of z plus w is that. And in this case, that's exactly equal to modulus of z minus w. So we get equality whenever z and w are diametrically opposed, pointing in the opposite directions. In any other case, you know, the z plus w is actually going to be strictly greater than absolute value of z minus absolute value of w. You can try and do these things geometrically by setting z equal to x plus iy and w equal to u plus iv, and I mean algebraically, and just grind that through, but that gets pretty tedious. Okay, so the next part is going to be about complex numbers in polar and exponential form.